All right, so if we're looking at complex numbers in polar form, let's kind of do a quick review of what we've talked about with complex numbers so far. What have we done related to complex numbers that y'all can remember? We've multiplied and divided complex numbers. What else? We added and subtracted complex numbers. We graphed complex numbers, and one other thing. What?
Wait, didn't we do that like
That's multiplication. We did the absolute value of complex numbers. Okay. Now, a couple of those things are going to be directly applicable to what we're doing today: the graphing part and absolute value. Okay. Now, so here is standard form of a complex number is a plus bi, where a is what we call the real component of the imaginary number, and b is the imaginary part. A is the real part of the complex number, and B is the imaginary component of the complex number. We graph that in the complex plane, where the real axis is the horizontal axis, and the imaginary axis is the vertical axis. Okay. What we're going to do today is we're going to transform this from complex standard form to polar form. So we need to know what polar form is. Okay, polar form of a complex number is, I can't write this. Polar form is, this is going to look worse than it is. Right? R cosine of theta plus I sine of theta. Now, but we need to determine, excuse me, I left something out. R times I sine of theta. And sometimes you see this written as R times cosine of theta plus I sine of theta. They'll factor out the R. Okay, now let's talk about the relationships here. In the complex plane, we have our real axis, which is related to which of these variables over here? Do what? Which one of these is related to the real axis? A is the real axis, right? So that's like our x coordinate, so to speak. And then we had the imaginary axis, and that was related to B, right? So we had real, imaginary, X, and Y. All right. Now, let's talk about the relationship between that in the, back in the regular coordinate plane, when we did our trig unit circle, and we graphed the circle around, we said that the x coordinate was related to what? Cosine. And the y coordinate was related to the sine. Okay, so cosine, sine. So cosine is related to the x coordinate, and y is the sine of the angle. So you can kind of still see that in the polar form of the complex number, our complex number is related to sine. The vertical axis in the coordinate plane is related to sine, right? The y coordinate is sine in the unit circle, and the x coordinate is related to the cosine. So we still have our real portion of our complex number and our imaginary portion of our complex number holding true. So we need to define what R is and what theta is. All right? We need to determine what R and theta is related to the complex number. So A plus bi is going to translate into R cosine of theta plus R times I sine of theta. And here's the definition of the variables. R is equal to the absolute value of A plus bi. which we define to be what? Square root of a squared plus b squared. Right? Theta is the inverse tangent of b over a, with an asterisk, because we have to place it in the correct quadrant. We have to place that angle theta in the correct quadrant. So we'll use the inverse tangent of b over a, and then we'll place it in the quadrant to get the angle correct. Okay, so let's let's do a few of these. Y'all ready? So what I want to do is start with. Can I erase this? Y'all okay with this? Let's start with 2 plus 2i.
This is the new Sam.
Yeah. 2 plus 2i. And what I want to do is I want to graph it, so I know what quadrant it's in, etc. 2 plus 2i. It's going to be right there. If this is my real axis and this is my imaginary axis. So to do the polar form, what I'm really looking for is the magnitude, the absolute value of that thing, which is its distance from there. And I need to know what this angle is. Okay, so this is 2 plus 2i, which means my real component is 2, my imaginary component is also 2. So what kind of triangle am I dealing with there if I have those values both being 2? It's a right isosceles triangle, which means it's a 45, 45, 90. So I know that my angle here is 45 degrees, or you could call it pi over 4 if we were dealing with radians. Okay, the magnitude, or the absolute value of 2 plus 2i is equal to, and we could do this the long way, or we could do it the short way. The short way is knowing that the hypotenuse of a 45, 45, 90 triangle is the square root of 2 times the length of the legs, so it's just 2 times the square root of 2. But you could do the square root of 2 squared plus 2 squared, that's 8. Square root of 8 is again 2 times the square root of 2. So that's my R value. My angle, theta, is pi over 4. Let's stick with degrees here, 45 degrees. All right. So 2 plus 2i is equal to 2 square roots of 2 times the cosine of 45 degrees plus 2 square roots of 2, we'll put the I out front, times the sine of 45 degrees.
Well, you see the 45 and put like the cosine or whatever in parentheses? Or do you want us to write it like that?
The other way you could write this, if you were writing this kind of in a different value, you could pull your R out front and do 2 square roots of 2 times cosine 45 plus I sine of 45.
Wait a second.
Yeah.
Where did you get the 45 from? Like, I understand, but like,
Well,
how does that go to the B over at the 10?
we didn't have to use that because this was a special right triangle, but you could use that. What is the, if you use your calculator to find the inverse tangent of B over A? What's the inverse tangent of 1? The angle whose tangent value is 1 is 45 degrees. And that's 45 degrees in the first quadrant, so 45 degrees is what we go with. Do what?
You can check that because it should equal 2 plus 2i.
That's exactly right. You can check this. The cosine of 45 degrees is what? Square root of 2 over 2. And that's I times the sine of 45 degrees, which is also the square root of 2 over 2. And when you multiply that out, you get this. So we're just writing this in an expanded form. And the reason it's important is because we have that angle. This is going to carry us into vectors. What are vectors? Vectors are quantities that have a magnitude and a direction. Okay, here is the magnitude, and here is the direction. The magnitude is the norm of the vector, the absolute value of the vector, the absolute value in this case of the complex number. The magnitude, how big is it? That's the magnitude, right? So a vector has those two quantities. It has a magnitude and a direction. The magnitude in this case is the r value, the direction is the theta value.
So our answer is that long version?
Either one of these could work as your answer, but there's going to be a step to the process. Okay, let's do another. Let's do let's do 1 minus 3i. I don't know what that is in polar form. 1 minus 3i. So let's start out by graphing because we need to kind of see this. I want you to be able to see the context. One minus 3i is going to be right there. Okay, so if I take this triangle here and kind of blow it up, make it a little larger, I'm dealing with this triangle where this is 1 and this is 3. So what do I have to know to write this in polar form? I need to know the absolute value and I need to know the angle. I kind of actually drew that triangle incorrectly, didn't I? Where do we want our triangles to always go back to? We want our triangles to go back to there. Yeah. So it would have worked, but. So this is the triangle we're working with here. So the absolute value of this is, the absolute value of 1 minus 3i is equal to the square root of 1 squared plus negative 3 squared, which is the square root of 10. So that's my r value. Now I just need to find my theta value and I'm done. So I need to know what angle that is. What angle is this? From here down to there. Or you could go, positive direction to get to it as well. It's the same thing. Negative. Okay, negative 71.6 degrees. Is everybody getting that same thing? So that's going to be my theta value. Theta is 71.6 degrees negative. And you get that by doing, in this case, the inverse tangent of b over a. What is the inverse tangent of negative 3 over 1? You plug that into your calculator, and it gives you, in this case, it gives you that actual angle, negative 71.6 degrees.
It's in the right one.
That's in the correct quadrant. Yes, it's good. We don't have to do any changing.
How do you know it's in the right one?
Because I can see it. This is the angle. It's in the fourth quadrant, right? And this is in the fourth quadrant, so I'm good to go. They agree. The next one won't be, so we'll have to place it, and you'll be able to kind of see. So to finish this out, this would be cosine of negative 71.6 degrees plus I sine of negative 71.6 degrees. So my complex number has a magnitude and it has a direction. Okay, so I'm expressing this in a vector format, a polar form for this. And then just like the unit circle, the cosine is our horizontal component and the sine is our vertical component.
So we wrote it with the thing on the outs, like factored in.
Yeah, I just wrote it that way just because it's a little,
Smaller.
yeah, it's smaller. It's concise. You don't have to write the square root of 10 twice. Okay, let's do another one. Y'all catching this? It's not too bad, right? Let's do negative 4 minus 3i. Now, can we do this without? Let's try doing this one without drawing it, and see what happens. Okay, let's just try it and see what happens. What's the magnitude of this thing? The magnitude, or the absolute value of 4 minus 3i, is equal to the square root of 4 squared plus 3 squared. That's 16 plus 9, which is 25, right? And that's the square root of 25 is, let's just we're 5. We're grown up, so we can do that. So that's my R value. So I know automatically now that this complex number is equal to 5 times the cosine of something plus I times the sine of something. And I got to find that something. And this is the part that's nearly impossible to do without drawing a picture. You just about can't do it, right? Because what is the inverse tangent? Our angle theta. Our angle theta is equal to the inverse tangent of b over a. That's negative 3 over negative 4. What is that? 36.7, but there's a problem, right? What's our problem? That angle's in the first quadrant. Where is this complex number? It's in the third quadrant, right? So I have to place 36.7 degrees into the third quadrant. So I'm going to have to graph this. So 36.7 degrees in the third quadrant is that angle. So what is that going to be? Plus 180, so that'll be 216.7 degrees. Right. So cosine of 216.7. I'll show you. I'm going to have to go back to the picture again there in just a second. 216.7, is that right?
It doesn't specify the graph. Do you care if we do or not for these?
I don't care if you do or don't, but the graph for most of you is going to be essential.
Okay.
It's going to be necessary. You understand where the 36.7 degrees came from, Sydney? Okay. Where is it?
It's in the first quadrant.
That's in the first quadrant. I need it to be in the third quadrant. So that 36.7 is always going to come back to the x-axis. That's my reference angle is always going to come back to the x-axis. So that's 36.7 degrees. And so to get it, yeah, this is, so the angle from standard position is, it's 180 plus 36.7, and that's what takes me down to there. And that's 216.7 degrees. Yes.
Is it the same thing if you were to find the actual fourth quadrant angle instead of finding the negative?
Absolutely. There's multiple answers to these things because we could be heading, the angle could be heading in a positive direction. And it really doesn't matter in your vectors, okay? So they can tell you, when we start really dealing with vectors, we're going to be talking a lot about north, south, east, and west, right? North, south, east, and west. So they might tell you it's 70 degrees south of east. Or they might tell you it's 20 degrees north of west. And we have to learn how to kind of place those in the correct quadrants, okay? 20 degrees north of west is this angle, right, which is 160 degrees. Yeah. It is physics. Vectors is physics. Okay? All right, let's do one more. And y'all think y'all are okay with one more and you can practice? Let's do, we did a first quadrant, we did a second. Did we do a second? Let's do we didn't do a second. Let's do -3 plus 5i. That's in the second quadrant, right? The radius or the r value of this thing, the magnitude of this is the square root of 3 squared plus 5 squared. That gives us 34. So that's my r value. How do I find the angle? Inverse tangent of 5 over -3. Inverse tangent of b over a, but I still have to place that angle in the second quadrant. So what is that angle? -59 degrees. That's a fourth quadrant angle. Is it -59 even?
0.03.
Yeah, we'll leave it -59, 0.03. We're not going to get that technical at this point. If we were dealing with vectors that were hundreds of miles long or had magnitudes of 500 or 5 miles, then we would want to keep the 0.03. We might want to keep 4 decimal places, okay, because it makes a difference when you're talking about large magnitudes. But we'll just leave this at -59 degrees for now. But that's headed in the wrong direction, right? It's exactly 180 degrees in the wrong direction because this is in quadrant 4, and where's my angle? This is in quadrant 2. So, quadrant 2, 59 degrees. What angle is that? 121. So, square root of 34, my angle theta is 121 degrees. So, square root of 34 times cosine of 121 plus I sine of 121 degrees. Let's put our degree symbol there. You can check this, right? Y'all want to check it? Take your calculator and do cosine of 121 and multiply it times the square root of 34. You're going to get something that's really, really close to -3. It's going to be a little off because we trimmed some decimal places off of our angle. But you can always multiply this out, and that's going to be part of the process we're going to use when we're given vectors in polar form. Guess what we're doing tomorrow? We're converting from polar form back to complex form, and then we'll start working with our vector operations on Thursday and Friday.
How do we know to add 180?